Hello and welcome to Fundamentals of Cybersecurity, CSCI150N. My name is Peter Keurig. I'm your instructor. This is Chapter 6, Public Key Infrastructure. In this chapter, you will learn how to implement the basics of public key infrastructure, describe the roles of registration authorities, use digital certificates, understand the life cycles of certificates, explain the relationship between trust and certificate verification, describe the roles of certificate authorities and certificate repositories, identify centralized and decentralized infrastructures, and describe public and in-house certificate authorities. For this video, we'll look at the basics of public key infrastructure, certificate authorities, registration authorities, digital certificates, certificate life cycles, certificate repositories, trust and certificate verification, centralized and decentralized infrastructures, public certificate authorities, in-house certificate authorities, and certificate-based threats. Public key infrastructure is made up of hardware, applications, policies, services, programming interfaces, cryptographic algorithms, protocols, users, and utilities that work together to allow communications to take place using public key cryptography and symmetric keys for digital signatures, data encryption, and integrity. A certificate authority is a trusted authority that certifies individual identities and creates electronic documents indicating the individuals are who they say they are. A digital certificate establishes an association between a subject's identity and a public key. Certification practices statements outline how CAs verify identities. The certificate server is the actual service that issues the certificate based on the data provided during the initial registration process. The server constructs and populates the digital certificate with the necessary information and combines the user's public key with the resulting certificate. The certificate is then digitally signed with the CA's private key. A registration authority is the PKI component that accepts a request for a digital certificate and performs the necessary steps of registering and authenticating the person requesting the certificate. The authentication requirements differ depending on the type of certificate being requested. A local registration authority performs the same function as a registration authority, but the local registration authority is closer to the end users. This component is usually implemented in companies that have their own internal public key infrastructure and have distributed sites. A digital certificate binds an individual's identity to a public key, and it contains all the information a receiver needs to be assured of the identity of the public key owner. Certificate extensions allow for further information to be inserted within the certificate, which can be used to provide more functionality in a public key infrastructure implementation. Certificate extensions can be standard or private. Standard certificate extensions are implemented for every public key implementation. Private certificate extensions are defined for specific organizations or domains within one organization, and they allow companies to further define different specific uses for digital certificates to best fit their business needs. Certificate extensions are considered either critical or non-critical, which is indicated by a specific flag within the certificate itself. When the flag is set to critical, it means that the extension must be understood and processed by the receiver. If the receiver is not configured to understand a particular extension marked as critical and thus cannot process it properly, the certificate cannot be used for its proposed purpose. If the flag does not indicate that the extension is critical, the certificate can be used for the intended purpose, even if the receiver does not process the appended extension. A CA certificate or a certificate authority certificate can be self-signed in the case of a standalone or root certificate authority. It can be issued by a superior certificate authority within a hierarchical model. A cross-certification certificate or cross-certificate is used when independent certificate authorities establish peer-to-peer trust relationships. Simply put, cross-certificates are a mechanism through which one certificate authority can issue a certificate allowing its users to trust another certificate authority. Within sophisticated certificate authorities used for high-security applications, a mechanism is required to provide centrally controlled policy information to PKI clients. This is often done by placing the policy information in a policy certificate. Like many other things in security, there is a life cycle to certificates. Registration and generation is the first step. A key, be it public or private key, can be generated locally by an application or by a central key generation server. The second step is the certificate signing request. Is the actual request to a certificate authority containing a public key and the requisite information needed to generate a certificate. The certificate signing request contains all of the identifying information that is bound to that key by the certificate generation process. The next step is renewal. At some point or another, that the certificate has a finite period of time that it is good for, or a lifespan. And then at the end of that life, you can choose to renew it to keep the same certificate, or you can choose to suspend it if you want to temporarily make that certificate unavailable. Finally, once it's been revoked, you want to destroy the key. The intention of doing that is so that nobody can unencrypt something that was previously encrypted using that key, or hash or whatever based upon that key, because it's no longer good, and you don't want people to get to previously encrypted messages or files. So certificate repository is a general term that describes a central directory that can be accessed by a subset of individuals. The directory usually uses LDAP, or is LDAP compliant, meaning that they can be accessed and searched via LDAP query from an LDAP client. So, for example, Active Directory is LDAP compliant, and you can use keys within an Active Directory context. So security is about being suspicious and being safe. We are supposed to be paranoid when we're doing this job. So automatically, we don't trust people we don't know. So in order to vouch or ensure that messages and data we're getting from people is from who they say they are, we need somebody who's a third party. And that's the certificate authority that we're talking about. And the way that it works is when a message is sent to us, let's say Joyce in this example sends a message in digital certificate to Maynard. Maynard extracts the certificate. A lot of times, for example, in Outlook, it's capable of doing it automatically. It puts the certificate through a hashing algorithm. The algorithm calculates a value. Maynard extracts the encrypted message digest from the certificate. Maynard decrypts the value with the certificate authority's public key, and Maynard checks to see if the certificate was revoked. If it's not revoked, if it's still current, then Maynard compares the value of A and B. The values are the same, so Maynard reads the message. So it's a valid message. So a public key infrastructure can be either decentralized or centralized. A decentralized approach, software on individual computers generate and store cryptographic keys locally to the systems themselves, and then the user shares their public key with whomever they want to share it with. With a centralized approach, the infrastructure, the keys are generated and stored on a central server, and the keys are then transmitted to the individual systems as needed. You might choose one type over the other for several reasons. First off, if you take a look at the two pictures here, with the decentralized, if you're giving out your public key to every individual, and they're all receiving public keys from each person that they know, it gets to be a lot of keys that they have to store locally. And when one person changes that key, then it doesn't. If they regenerate a new key, they now have to retransmit it to everybody in that little web. So it can get very complicated the more people you have involved in the web. You're looking at the second diagram. This is the centralized approach, where everybody's key is generated in the middle, and a public key for everybody else they want to talk to. They pull as needed from that centralized location or repository. So if there's a change, if somebody gets a new key because a previous key is revoked or expired, they get the current key from that. So one of the approaches to a centralized public key infrastructure is hardware security module, which is basically a physical device that safeguards cryptographic keys. Hardware security modules enable a higher level of security for the use of keys, including generation and authentication. In most situations, hardware security modules solutions are used only for the most critical and sensitive keys, which are the root keys and possibly the intermediate certificate authority private keys. So protecting the private key is one of the most important things in the public key infrastructure. The private key needs to stay private. A digital signature is created solely for the purpose of proving who sent a particular message by using a private key. When a private key is generated for the first time, it must be stored somewhere for future use. This storage area is referred to as a key store and is usually created by the application registering for a certificate such as a web browser, smart card software, or other applications. In most implementations, the application will prompt the user for a password, which will be used to create an encryption key that protects the key store. So key recovery. The fact is sometimes keys get lost, or if you get a new key and you have an old file or email or something of the sort that's encrypted that you need to read that you can't with the new key because it's encrypted under the old one, you need to be able to recover your previous keys. So short of it being destroyed, as we talked about in the life cycle earlier, if you still have the key, you can recover it. One individual can have one, two, or many key pairs that are tied to his or her identity, or even more over the lifetime of a person's career. That's because the user may have different needs and requirements for public and private key pairs. If a company is going to perform key recovery and maintain a key recovery system, it will generally back up only the key pair used to encrypt data, not the key pairs that are used to generate digital signatures. Two systems are important for backing up and restoring cryptographic keys: key archiving and key recovery. Key archiving is a way of backing up a key and securely storing them in a repository. And then key recovery is the process of restoring the lost key to the users or the company. Dual control can be used as part of a system for backup and archiving data encryption keys. PKI systems can be configured to require multiple individuals to be involved in any key recovery process. When a key recovery is requested, at least two people can be required to authenticate by the key recovery software before the recovery process is performed. This enforces separations of duties, which means that one person cannot complete a critical task by himself, and requiring two individuals to recover a lost key together is called dual control, which simply means that two people have to be present to carry out a specific task. So key escrow and key recovery are terms that are often used interchangeably, but they are actually describe two different things, and you should not use them interchangeably. Key escrow is the process of giving keys to a third party so that they can decrypt and read sensitive information if the need arises. Key escrow also always pertains to handing over encryption keys to the government or to another higher authority so that the key can be used to collect evidence during investigations. A key pair used in a person's place of work may be required to be escrowed by the employer for two reasons. First, the keys are property of the enterprise, issued to the worker for use. Second, the firm may have need for them after an employee leaves the firm. So, for example, somebody leaves and they've archived critical data, the firm has a right to retrieve that data afterwards. A public certificate authority specializes in verifying individual identities and creating and maintaining their certificates. These companies issue certificates that are not bound to specific companies or inter-company departments. Instead, their services are to be used by a larger and more diversified group of people and organizations. If a company uses a public certificate authority, the company will pay the certificate authority organization for individual certificates and for the service of maintaining these certificates. Some examples of these public certificate authorities are VeriSign, Entrust, and GoDaddy. A certificate policy allows a company to decide what certification classes are acceptable and how they will be used within the organization. Opposite of the public certificate authorities, in-house certificate authorities is implemented, maintained, and controlled by the company that implemented it. This type of certificate authority can be used to create certificates for internal employees, devices, applications, partners, and customers. This approach gives the company complete control over how individuals are identified, what certification classifications are created, who can and cannot have access to the certificate authority, and how the certificate can be used. So when a company has decided that they don't want to use a public certificate authority and they don't have the technical know-how or capability for in-house certificate authorities, their last available option is to outsource different parts of it to a specific service provider. Usually the more complex parts are outsourced, such as the certificate authorities, the registration authority, and the certificate revocation list and key recovery mechanisms. This occurs if a company does not have the necessary skills to implement and carry out a full PKI environment. And the diagram next to it kind of shows 4 different ways it can be done, where either individual components or all 4 of those components could be outsourced based upon the needs of the company. In some cases, more than one certificate authority may be needed for a specific public key infrastructure to work properly, and several requirements may be met for different public key infrastructures to intercommunicate. Here are some examples. A company wants to be able to communicate seamlessly with its suppliers, customers, and business partners via public key infrastructure. One department within a company has a higher security requirement than all the other departments and thus needs to configure and control its own certificate authority. One department needs to have specially constructed certificates with unique fields and usages. Different parts of an organization want to control their own pieces of the network and the certificate authority that is encompassed within it. The number of certificates that need to be generated and maintained would overwhelm one certificate authority, so multiple certificate authorities must be deployed. The political culture of a company inhibits one department from being able to control elements of another department. Where enterprises are partitioned geographically and different sites need their own local certificate authorities. For all this to work, there must be trust models. A trust domain is a construct of systems, personnel, applications, protocols, technologies, and policies that work together to provide a certain level of protection. Potential scenarios exist other than just having more than one certificate authority. Each of the companies or each department of an enterprise could actually represent a trust domain itself. Different trust domains are usually managed by different groups of administrators, have different security policies, and restrict outsiders from privileged access. Most trust domains usually are not islands cut off from the world. They need to communicate with other, less trusted domains. The trick is to figure out how much 2 different domains should trust each other, and how to implement and configure an infrastructure that would allow these 2 domains to communicate in a way that would not allow security compromises or breaches. So the first model is the hierarchical trust model. The hierarchical trust model is a basic hierarchical structure that contains a root certificate authority, an intermediate certificate authorities, leaf certificate authorities, and end entities. The configuration is that of an inverted tree. The root certificate authority is the ultimate trust anchor for all other entities in the infrastructure, and it generates certificates for the intermediate certificate authorities, which in turn generate certificates for the leaf certificate authorities, and the leaf certificate authorities generate certificates for the end entities, that being users, network devices, and applications. With the hierarchical trust model, endpoints must be able to walk through the certificate path. In other words, follow the certificate path means tracking down and collecting certificates until it comes upon a self-signed certificate that indicates that it was signed by a root certificate authority. So in this particular diagram, Debbie wants to validate that Sam's certificate is authentic. So both of them have certificates that were signed by their leaf certificate authorities. In this case, Sam's was Leaf D. His certificate was signed by the Leaf D certificate was signed by the intermediate B, which the intermediate B certificate was signed by root CA. Basically, the software on Debbie's machine traces it all the way back to the root CA. Once it finds that that is a valid root certificate authority, it trusts Sam's certificate is authentic based upon that path that it walked all the way back. The second trust model is the peer-to-peer model. In a peer-to-peer trust model, one certificate authority is not subordinate to another certificate authority, and no established trust anchors between the certificate authorities is involved. The end entities will look to their issuing certificate authorities as their trusted anchors, but the different certificate authorities will not have a common anchor. The two different certificate authorities will certify the public key of each other mutually, which creates a bidirectional trust. This is referred to as cross-certification. Since the certificate authorities are not receiving their certificates and public keys from a superior certificate authority, but instead are creating them from each other. The issue becomes here is when you have multiple peer-to-peer models. It goes back to when we were talking about the decentralized keys versus the centralized key management. The web, as you can see in the bottom diagram, starts to get huge, and a lot more peer-to-peer relationships have to be generated. In turn, when a certificate expires or is revoked, or a key needs to be changed, now you have to reestablish that peer-to-peer trust with each one of those certificate authorities in the mesh. So a third trust model is really a hybrid of the first two. The two companies have their own internal hierarchical models and are connected through a peer-to-peer model using a cross-certification. Another option in this hybrid configuration is to implement a bridge certificate authority. A bridge is responsible for issuing cross certificates for all connected certificate authorities and trust domains. The bridge is not considered a root or a trust anchor, but merely the entity that generates and maintains the cross certifications for the connected environments. So we turn to certificates for our security in order to secure things through authentication, integrity, and confidentiality with keys. However, there are threats that come along with certificates. Certificates act as a form of trusted ID and are typically handled without end-user intervention. So, for example, when you install software directly from Microsoft, the operating system, the Windows operating system, trusts the software that is signed by Microsoft's certificate, and therefore doesn't ask you to validate or verify the certificate and that the authenticity of the software. So there have been stolen certificates have been used in multiple cases for computer intrusion and system attacks. Examples of those are the Stuxnet attack, the Sony Pictures attack, and also the Microsoft attack, where two of their signing certificates for their software were stolen and used to produce malware. Specifically created malware has been designed to steal both private keys and digital certificates from machines. An example of that is the Zeus botnet. One of the things it looked for was your any certificates on your system as well as private keys, in which case it would send it back to its command and control to be used by whoever it is controlling that botnet. I'm your instructor, Peter Keurig, for Nashville Community College. Thank you for watching.